Hydraulic systems can operate at extremely high pressures and can cause serious injury or equipment damage if handled improperly. Always ensure you are properly trained and follow all applicable safety procedures before working on any hydraulic system. Directional valves come in many different sizes, configurations, and spool designs. At first glance, all the symbols, ports, and flow paths can seem confusing. But once you understand the basic principles, they're actually quite simple. In this video, we'll break everything down step by step and remove the confusion so you can understand exactly how directional valves work. In this video, we'll start by looking at the main components that make up a hydraulic directional valve. Then we'll see exactly how directional valves control the flow of hydraulic oil within a system. Next, we'll cover the most common types of directional valves and explain how each one works. We'll also discuss the typical valve sizes you'll encounter in industry and the flow rates they're designed to handle. And as a bonus, we'll finish by looking at some of the most common directional valve problems and failures, along with what causes them. A hydraulic directional valve consists of three main components: the valve body, the ports, and the spool. The valve body is the main housing that contains all the internal components and is precision machined to allow the spool to move smoothly while directing hydraulic fluid through the correct flow paths. In this example, we're using a two-way directional valve. It's called a two-way valve because it has two ports, port P and port A. When the spool moves to the left, a movement known as a spool shift, it opens a flow path between the two ports, allowing hydraulic oil to flow from port P to port A. One thing I've learned from years of working with hydraulic and electrical systems is that understanding a concept is very different from memorizing it. Anyone can memorize a valve symbol or remember which port goes where. The real challenge is understanding why the oil flows the way it does and how the entire system works together. That's exactly why I've been using Brilliant's new tutor. Instead of simply giving you answers, it works through problems with you and adapts to the way you think. It can draw diagrams, ask guiding questions, and help you understand the reasoning behind a solution, almost like having a personal tutor sitting right beside you. What I like most is that you're actively solving problems. You're not just watching videos or reading explanations. You're learning by doing. Brilliant's courses cover everything from middle school math all the way to advanced college-level topics and coding. The lessons are designed by experts from MIT, Harvard, and Stanford. Whether you're a student, engineer, technician, or simply someone who enjoys learning, Brilliant helps build the problem-solving skills that apply to almost every technical field. You can try Brilliant's new tutor for free using the link below. And Electrical Lad viewers can get 20% off an annual premium subscription. Scan the QR code or visit brilliant.org/electricallad to get started. So how do we operate a directional valve? There are several common methods to accomplish this, including levers, foot pedals, solenoids, pilot-operated systems, and solenoid-controlled pilot-operated. Each method has its place in the industry, chosen based on the size of the valve and the system's requirements. Now let's go back and focus on the directional valve in our hydraulic system. This is called a four-way valve because it has four ports. P is for pressure, where the fluid enters. T is the tank port, where the fluid returns to the reservoir. A and B are the working ports that connect to the actuator to control its movement. The valve is also known as a center-blocked valve because when the spool is in the center position, it blocks all four ports. Additionally, this is a solenoid-operated valve because the spool shifts to positions A or B when a solenoid is energized. The valve uses springs to return the spool to its neutral center position. Now that we've covered the basics, let's break it down. This is a four-way, three-position, solenoid-operated center-blocked valve. Let's see how it works. When the valve is in the neutral position and no solenoids are energized, the spool is centered, and the ports are blocked. When solenoid A is energized, the spool shifts to the left, directing pressure from port P to port A and connecting the tank port T to port B. This action causes the cylinder to extend. In the next clip, pay close attention to the valve operation to see how this process works. An important practice is to de-energize the solenoid A once the cylinder is fully extended. This ensures the cylinder stays extended until solenoid B is activated. Note that this applies only to valves with center block positions. Now let's talk about retracting the cylinder by energizing solenoid B. Let's start again with the cylinder fully extended and the directional valve in its center position. When solenoid B is energized, the spool shifts to the right, connecting pressure port P to port B and port A to the tank. This causes the cylinder to retract. In the next clip, pay close attention to the valve operation to see how this process works. It's time to discuss the different styles of valves. Understanding valve variations is essential when working with hydraulic schematics and design applications. Let's break it down step by step to make it clear and easy to follow. First on the list is the tandem center valve. In its neutral position, the pump port connects to the tank port, allowing fluid to flow freely back to the reservoir. At the same time, the work ports A and B are blocked, preventing any movement in the actuator. This setup helps save energy by letting the fluid return to the tank without forcing it to pass through the relief valve at the system's set pressure. The downside of a tandem center valve is that the pump can only supply the circuit with the tandem center. It can't be used for other circuits because when the valve is in the center position, the pump pressure drops to nearly 0 psi. This means the pump isn't building pressure to operate anything else while the valve is centered. Next is the open center hydraulic valve, also known as an H-center valve. When the valve is in the neutral position, the work ports are open to the tank, meaning the actuator isn't locked or held steady. It's free to move if there's an external force acting on it. At the same time, fluid flows freely from the pump back to the tank, which reduces pressure to nearly zero. Like the tandem center, this setup is great for reducing strain on the pump, but it's limited to a single circuit. Next, let's talk about the float center hydraulic valve. In its neutral position, the work ports connect directly to the tank, allowing the actuator to move freely under load without resistance. Unlike tandem or open center valves, the float center valve doesn't route pump fluid back to the tank when centered. This design allows the pump to operate multiple circuits, as the fluid flow isn't diverted. There's one more commonly used valve worth mentioning, which doesn't have a center position: the four-way solenoid-operated spring return valve. In operation, when the solenoid is energized, the actuator will either extend or retract depending on how the valve is configured within the circuit. Once the power is turned off, the spring mechanism takes over, causing the actuator to reverse direction and return to its original position. As hydraulic directional valves get larger, the force required to shift the spool increases dramatically. D03 and D05 valves are typically direct operated because the solenoid can generate enough force to move the spool directly. D07 valves fall into a transition range and may be either direct operated or pilot operated depending on the flow and pressure requirements. Once we reach larger valves such as D08 and D10, pilot operated designs become the norm. In these valves, the solenoid controls a small pilot stage, which uses hydraulic pressure to shift the main spool. This allows the valve to handle much higher flow rates and pressures. Now that you understand how directional valves work, let's look at two of the most common problems that cause them to malfunction, and more importantly, how to prevent them. Directional control valves have very tight metal-to-metal clearances. When contamination gets into the system, those metal particles can scratch the internal surfaces. Over time, that work creates internal leakage, and valve will operate properly or hold pressure in the correct port. Properly designed hydraulic system should have two filters, a suction filter and a return line filter. The suction filter protects the pump by preventing large contaminants from entering the system. Another common concern with directional valves is the solenoid coil. Many industrial coils are rated for continuous duty and can remain energized for long periods. However, they still generate heat whenever power is applied. For this reason, it's good practice to de-energize the coil when the valve is no longer needed. In applications using a single solenoid spring return valve, the coil must remain energized to keep the valve shifted. Excessive heat from overvoltage, high ambient temperatures, or an incorrect coil can eventually damage the insulation and cause the coil to fail. Thanks for watching. If you found this video helpful and want more practical, real-world electrical and hydraulic lessons, be sure to subscribe, give us a thumbs up, and turn on notifications so you never miss a new electrical lab video.